Hi, welcome back. So lecture 14, today we'll be looking into chapter 6. We'll be talking about Gauss's law. It will be the first lecture on Gauss's law. We'll probably need 2 lectures on this topic. So let's take a look on this chapter. So first, let's define a term called electric flux. So this is a measure of electric field perpendicular to a surface. So it's basically how much electric field goes through a surface in that sense. Okay, so the definition of it will be mathematically, that is E field, which is vector dot product of the area of the surface that's in the normal direction of it. So this is a vector called A area vector, which is having the magnitude of the area, but in the direction of the normal direction of the area. Okay, so for a flat surface, so then this is a constant vector. Okay, we'll talk about on not flat surface, uneven surfaces later on, but for right now, focus on flat surface. So in this case, you can see E and A vectors, they are dot product. So the magnitude then will be EA cosine theta. Okay, and because the dot product will be a scalar, so it will not have a direction as a result. So electric flux is a scalar, is a dot product of 2 vectors, electric field, and the vector area vector of the surface, particular surface. So it depends on the E and A if they have an angle of theta. So general expression EA cosine theta. Okay, so in this case, if E and A are in the same direction, so that means E is perpendicular to the surface, where normal direction of the surface is perpendicular to the surface. So E and A in the same surface, so then the magnitude will be just E times A. Now, in the case if you have a surface like this one here, makes the angle with the E field of theta. So this will be E, and the angle theta will be E mixed with the normal direction of the surface. Okay, so M. So in that case, so then EA cosine of theta. Okay, the SI unit for electric flux is newtons times meters square over coulomb. Newtons over coulomb is the unit for the electric field. Area is in meters square. Okay. So for a particular surface, you can think about 2 normal directions, right? The one side of the surface, the normal direction will be pointing in that direction. The other side of the surface is pointing in the other direction. So there are actually 2 directions for the vector A. So when you are calculating electric flux, if you have an enclosed surface, then the area vector is pointing from the inside to the outside of the surface. So think about like if it is a sphere, okay, so its normal direction A vector will be pointing outward, not inward, okay, in that sense. All right. For open surface, it could be either, okay, so I'll just put that out. But for a closed surface, there's a particular direction in that sense. Let's take a look at a couple of examples here. So the first one, it says calculate the flux through a square sheet with side of 2.0 meters if the plane of sheet is at angle 60 degree with a uniform electric field of magnitude of 1.1 times 10 to the 4. Okay, so let's sketch this problem. And we'll try to solve for this one. So the problem states that the square sheet, right? And that's a uniform field. So let me just draw the uniform field first. Horizontal field. And this sheet makes an angle of 60 degrees with this guy. So the sheet is something like that. Okay. So the sheet is in this direction, and then the electric field is in that direction. And it says these two makes an angle of 60 degrees. Okay. So calculating flux, right? Phi equals to E dot A, which is a vector of EA cosine of theta. So you can say, okay, my E is 1.1, 10 to the 4th newtons over coulomb. My area, right, for the square sheet should be 20 by 20, 2.0 by 2.0. Cosine of 60 degrees? Actually not. Actually, it should be 90 minus 60, okay? Remember, this angle will be the normal direction of the sheet. So this is the normal direction of it. Mixed with the E field. So this is E field, that's normal direction. So it'll be 90 minus that. So this guy will be 90 minus 60, which is 30 degrees, okay? So that's the catch there. So always remember, it's the normal direction of the surface makes the electric field. All right, so with that, this gives you 3.8 times 10 to the fourth newtons meter square over Coulomb. Okay, so that's the electric flux on this one. And let's go back to the slide quickly, and we'll be coming back. So the second problem here, it says, consider the uniform electric field, E field. Now this in given in components. And what's the electric flux through a circular area of 2.0 meters that is lays in the XY plane? Again, let's sketch this guy. Oh, let me stop sharing the screen so you can see the paper in the wider screen here. Okay, so E field. So this looks like a three-dimensional problem. So X direction, Y direction, and Z direction. Okay. X, Y, Z. So there's a circular area of 2 meters radius. So in the XY plane, so something like that here, where the radius 2. So this is 2 meters. The E field is in J and K direction. So for J is 3K. So it'll be something like this. And here, that's the E field. E field will be in that direction. E field, okay? And then you can imagine this is uniform E field in that direction. All right. So again, we are going to do flux equal to E dot A. Okay, so in this case, I think we can use the vector dot product here. So to get a magnitude. So vector dot product, if you have A dot B, is equal to A magnitude B cosine theta. Or let me just give you a quick review here. A dot B, right, would be equal to magnitude of A, magnitude of B, cosine of theta, the two mix. Or it could be equal to AX, right, BX plus AY, BY plus AZ, BZ. Okay, so that's a quick review. So we have used this one in the first one, in the first problem. Now we'll actually use this because the vectors are given in components, right? So for the E is 4.0 J plus 3.0 K. For the area, its radius 2, so the area will be pi times 2.0 meters squared, right? That's the area, but the directional of this area vector should be in the normal direction, right? So if the circle is in the XY plane, so the direction then will be in the Z direction, okay? So that will be then in K direction, okay? So you have A dot this second vector, okay? The first vector dot B, A vector dot B vector, all right? So AX is 0, all right? So then that term is 0. AY is 4, but BY is 0 because B vector is only in the Z direction, okay? So that's also 0. So then you'll just have to care about Z direction of A times Z direction of B. So then it'll be 3.0 times pi times 4.0 meters squared, okay? And then the first one, oh, that's the E is actually 10 to the third newtons over Coulomb. So 10 to the third newtons over Coulomb, okay? So this then will give you 12 because, yeah, 3 by 4 will be 12. 12 pi, okay, 10 to the third newtons meter square over Coulomb. Okay, and that will be your flux. Okay. All right. Now let's get back to the PowerPoint slide. If you have an enclosed surface, okay, so let's say the surface of this cube shape, and then you have E field in the direction of these red arrows, right? So we know if for enclosed surface, right, the pointing outward to be the normal direction, to be the positive direction of the surface, A vector, right? So then on the top surface here, the square of FGHK that have the A vector in the same direction of the electric field, right? So then that gives you a positive flux. At the bottom here, the positive direction for the area will be pointing downward. So then E field and that will be in the opposite direction. So this ABCD square, the flux through it will be a negative. So negative and positive actually will cancel, okay, in that case. The side fields, they are perpendicular, all perpendicular to this one. So then the normal direction of those sides and the electric field are perpendicular to each other. So then they actually give you zero flux, okay? So in that sense. So overall, the flux through this cube will be equal to 0, okay? Now for uneven surface, okay? So because surface is uneven, so then you have to slide the surface into small patches. So each small patch will have an area of delta A, and then with the vector form here, so then there's the normal direction of that specific surface, small patch of it, okay? So the E times delta A, or E dot delta A in that sense. And then you'll be just summary over through all the patches on the surface, okay, to get the total flux through that surface, okay. Now, because we are sliding the patches into small pieces, so then you can see, you can actually, in that case, if you can slice the small patches small enough, so then you'll be actually essentially doing integration, okay? So then for open surface, you'll then integrate through the whole surface of E, so delta A becomes derivative of A in that case, okay? So then you normally would do the integration and sub S through, that means you integrate through the whole surface, okay? And then if you have a closed surface, so it's the same thing, you are doing integration to the closed surface, all right? And then E dot derivative of A. But if you are integrating through a closed surface, then usually for the integration sign here, you put the circle at the center. That means you are integrating through the closed surface. But the mathematical operations they are the same, okay? It just indicates this is integrating through the closed surface and this guy is the open surface, okay? All right. So let's take a look on this example here. There's a point charge here, and there's a spherical surface enclosed there. The charge is placed on the center of the sphere. Okay. So then what would be the flux through the spherical surface? So basically, with the sphere has a radius of r. So in this case, let's take a look. Let's take a small portion on the spherical surface, derivative of A, and then its direction, this should be in the radial direction, right? Because it's the sphere. So pointing from the center of the sphere to the surface outward. The electric field by the point charge, we can calculate, right? Because this is point charge, so that will be K, which is 1 over 4 pi epsilon naught, Q over R squared. R will be capital R then, because that's the distance from here to your point of interest. And then times in this radial direction unit vector of R. So that's the direction of it, okay? So then the flux to this small area should be E at this particular point, right? Dot normal direction times the derivative of A. So these two together is the surface, the area vector, the A with the arrow, but derivative of A with the arrow, okay? So the amplitude will be derivative of A, but the direction will be in the normal direction of that particular surface. E is this guy, so you plug in that here in the place of E, you get this one. Where small r becomes capital R because the distance is capital R. Normal direction, unit vector will be the radial direction r prime, okay, or r to the hat, and then dA. So you have the two same, the electric field are in the same direction as the normal direction of the surface. So these two unit vectors dot becomes 1. So this is basically 1. So then you have 1 over 4 pi epsilon naught q over r squared derivative of A. Integrate through the whole surface, then it will give you the net flux. So integrating through that gives you net flux. Now everything is constant, right? This is K constant. Q is the charge of that. That doesn't depends on the surface. R is the radius of surface, so it doesn't change as well. So that means yeah, you can put everything in front of integral. Here you are integrating through the closed surface. So that's the sign says derivative of A. So that is basically the surface of the sphere, right? So 4 pi r squared. So this integration then gives you 4 pi r squared. So r squared cancels 4 pi and 4 pi cancel. So at the end, you have q equal to epsilon naught, okay? So this result shows you that the electric flux through a sphere that encloses a charge in this case, right? So in the middle of the sphere, actually is equal to just the charge divided by epsilon naught, which is the dielectric constant of vacuum. Okay, epsilon naught is a dielectric constant of vacuum. We have talked about that at the beginning of the electrostatic interaction. So that is 8.85 times 10 to the minus 12. Okay, that's the unit in SI unit. So flux then actually equals to Q over epsilon naught, okay? So then this is actually not just applying to the spherical has the charge inside at the center. It could be charged at anywhere just as long as it's enclosed by the surface. And as long as the surface doesn't necessarily have to be a sphere. It could be a cubic, could be a whatever shape, irregular shape, but as long as it enclose that charge. So then everything in every scenario, if a closed surface there's a charge inside, then the electric flux due to that charge, because there will be electric field due to the charge, right? Should be equal to the charge enclosed divided by the epsilon naught. Okay. So this is then the Gauss's law. So Gauss's law says the flux of the electric field through any enclosed surface is equal to the net charge enclosed divided by the permittivity of free space, okay? Epsilon naught. And that surface is called Gaussian surface, okay? So yeah, so you can just call it Gaussian surface. So if it's a Gaussian surface, that means it has it actually encloses some charge there, okay? So mathematical expression, the Gauss's law, flux equal to integrating through the enclosed surface and electric field dot normal direction of dA equal to Q enclosed divided by epsilon naught. Let's take a look a few scenarios. Okay, so if you have a irregular shape like this, but it's an enclosed surface, it has an enclosed like a surface. Okay, outer surface of this body. Now, if there's a charge outside of it, so then this surface, enclosed surface, the flux through it will be equal to 0. So you can calculate mathematically, you can calculate the flux by electric field due to this charge, right? So that's the electric field. But through this side of the body, it will give you negative flux. And then through the other side of the body, it will give you positive flux because E field and normal direction are in the same direction. In this case, normal direction and E field are in the opposite direction. So negative flux, positive flux. But that will cancel out, okay? So for every electric field line, you can see through the body, there's a part on one side and then there's a part on the other side. So these two sides gives you positive and negative flux that cancels out, okay? So any of those lines would do the same. For the case of B, so if you have positive Q and then the equal negative Q and then enclosed by this surface, so then the electric field indicated by the electric field lines, the Q in charge enclosed now is a positive plus or minus. So that's also a 0. Okay, so in this case, then the flux should be also 0 because on this side you'll have positive flux, on this side you'll get negative flux. So overall, they will cancel out again. Okay. And on this, another scenario here, so you can think like the blob here as enclosed surface. There's a charge inside it. So then in this case, will be simply equal to Q of the charge over epsilon naught. Okay. And it doesn't depend on the shape or the size of it. If it's bigger, the area is bigger, but the electric field actually becomes smaller. Okay, so in that sense, if it's closer, smaller volume, or resulting small surface, but electric field at that surface will be stronger. So at the end, it will be the same. Okay, so it doesn't depend on the shape of the surface. Doesn't depend on the size of it either. Okay. If you have a surface enclosed a positive charge, then at the end you got epsilon over on the positive flux because Q over epsilon now will be positive. If you have a surface enclosed a negative charge, then the flux will be negative. Okay. Let's take a look on this example here. It says find the electric flux through the enclosed surface where cross sectionals are shown in the figure. Okay, so there are three different scenarios here. Let's take a look at them one by one. All right. So for A, you are going to apply the Gauss's law. So flux equal to Q enclosed divided by epsilon naught. All right. So this would be equal to, for this surface, there's only a positive charges enclosed by that surface. Okay. So this is cross-sectional area. So think about this as a blob. So enclose that. So then you just plug in that 3.0 times 10 to the minus 8 coulombs over epsilon naught 8.85 times 10 to the minus 12. That is in the units of Coulomb square over Newton meter square. Okay, that gives you 3.39 times 10 to the third Newton's meter square over coulombs. Okay, the negative charge is not enclosed by the surface, so that doesn't count. In case of B, right, there are three charges, but the surface doesn't include any of them. So then that flux will be equal to 0. Okay, because Q enclosed is 0. In case of C, you have minus Q. So then Q enclosed over epsilon naught, that is a minus 2.0 times 10 to the minus 6 over 8.85 times 10 to the minus 12 C square over Newton meter square. Okay, so that gives you 2.26 by minus times 10 to the third Newton's meter square over Coulomb. Okay, so you can simply just use the Q enclosed divided by epsilon naught for the flux. All right. Now let's take a look at the application, further application of Newton of the Gauss's law. Okay, to find, so in this case, to find the electric field at a particular point of interest. Okay, so for a Gaussian surface S over which the electric field has constant magnitude, so that's the first thing. So you want to be creative when you are doing this. So you want to, if you are looking at electric field at a certain point, you want to create a surface that the electric field, any point on the surface is going to be constant. Okay, so then that will help you calculate the electric field by simply using Gauss's law. So using Gauss's law, you can calculate this flux is equal to Q over epsilon naught, right? And then it's also equal to E times area. So if E is constant, then you just have to calculate the area. So then Q over epsilon naught over A, that will give you the E field. Okay. So looking at this example first, a quick one. So if you have a charged particle, right, at the center over here, all the charges on this sphere over here. So if you want to look for an electric field at this point, right? So now this time it's not necessarily a point charge, but it could be a charge distribution. Okay, so now it's a sphere distribution of charge. What will be the electric field at that point where this distance is r? So you can draw a sphere with the center at this guy with the area, a radius of r. So then enclose this charge distribution, spherical charge distribution. Okay. So then at any point over there, E field is going to be the same. because it's the same distance from the center of this charge is spherical. Okay, so um, in Gauss's law, we talk about if you have a uniform charge distribution of sphere, then you can actually treat as a electric field at the point of center. Okay, so in a sense, it will be constant. But let's see how we can solve for the E in this case. So E field over here, it will be a constant through that, all right? And you can then put this in front of integral. So then you are just integrating through the sphere. Integrating through the sphere, that gives you 4 pi r square for the area of it, right? So EP times 4 pi r square. And that should be also, according to Gauss's law, is equal to Q enclosed divided by epsilon naught. So then you can calculate E then by rearranging the terms, everything divided by, or both side equation divided by 4 pi r square. And that gives you electric field, okay? So electric field then has a magnitude of 1 over 4 pi epsilon naught Q enclosed divided by r square. And then if you can calculate the Q enclosed here, you can calculate the magnetic field, okay? Or the electric field of the Gaussian surface there. Now, what if you want to find an electric field inside your charge distribution? Okay, so inside charge distribution, you can also draw a Gaussian surface where this is from the center of the sphere, r distance away, small r distance away. Now, in this case, you have capital R. For outside the sphere, we calculate from the previous problem. So for outside the sphere, right, you get this equation. That's what we had earlier. Now inside the sphere here, so because your sphere Gaussian surface is smaller, then you just need to count the charges that enclosed by this. So outside here, charge outside here does not count. Okay, so then Q total, you just need to calculate Q total again, and then do the same thing as what we did for the R greater than, small r greater than capital R in the previous case. Okay, so then you'll get calculated a new Q within the small spherical shape there. Let's take a look at example here for this guy. So this one says using symmetry to calculate the E with Gauss's law. This is a non-conducting sphere of radius 6.00 centimeter, has a uniform volume charge density of 450 nanocoulombs per meters cube. Find the electric field at the following distance from the sphere's center: 2 centimeters and 10. So one is inside, one is outside. Okay. So let's draw this charge distribution. So imagine this is a sphere that has a radius of 6. So r equal to 6 centimeter. Okay. Sphere have a radius of r equal to 6. All right. Now we are looking for two scenarios. One is inside it. You can draw now a Gaussian surface sphere. Okay, so in this case, small r is equal to 2 centimeter. And then another scenario is capital R equal, or small r equal to 10. So for part B, let's look at part A first. So because it is a sphere, uniform distribution of charge, so then on the surface here, E field should be uniform throughout, or actually will be having the same magnitude. Okay, I shouldn't say uniform because it's vector. Direction will be different, but magnitude is the same. So then, according to Gauss's law, you can integrate through the this would be dot and then so E and N are in the same direction. Okay, so then just take the magnitude out. So then this would be just magnitude and then derivative of A. Now E is constant, so E integrated through the whole surface, Gaussian surface. Okay. So then this will be the area of that small sphere. So E times 4 pi r square. Also, Gauss's law says flux is going to be equal to Q enclosed divided by epsilon naught. the Q enclosed here should be equal to the density, charge density times its volume, okay, and over epsilon naught. Volume for this guy, for a sphere, so it will be 4 over 3 pi r to the q over epsilon naught. All right, so phi is equal to that, it's also equal to that, so you can set the two equal to each other. E times 4 pi r squared equal to rho times 4 over 3 pi r to the q over epsilon naught. Okay, so you probably realize there could be cancellation. 4 pi and 4 pi will cancel. Pi squared will cancel the q, or r squared will cancel the q, leaving r there. So it looks like E. So for pi a, E is equal to rho times r over 3 times epsilon naught. Okay. All right. So then after that, you can plug in your numbers. 450 nano, 10 to the minus 9, coulombs over centimeter cube, and the radius of 2.00 centimeters, so 10 to the minus 2 meters over 3 times 8.85, 10 to the minus 12, c square over n times meter square. Okay, so that gives you electric field as 3.39 times 10 to the second. Okay, so that's your A. And your B, now in this case, you would do similar. Okay, so you'll start with that. So again, and this one, but you'll just stop over here. Okay, or actually, let's do it there, the full solution here. So the first, apply Gauss law, integrations through E and dA. They are in the same direction, so then just the E will come out as a constant, integrates to the surface. So E times again 4 pi r squared. According to Gauss law, Q enclosed over epsilon naught, so that's rho V over epsilon naught. Now in this time, the charge distribution is only up to the sphere, right? Here is vacuum, nothing there. So you wouldn't use 10, the small r, but you would use the bigger R for that. So 3 times 4, or rho times 4 over 3 pi capital R to the Q, okay, over epsilon naught. All right, and then you're going to set these two together because they are both phi. Okay, so you're going to say E times 4 pi r squared equal to rho 4 over 3 pi r to the Q over epsilon naught. Again, there's some cancellation here. At this time, only 4 pi, because this is small r, this is capital R, they do not cancel. Okay, so this tells you that E is equal to rho r to the Q over 3 times epsilon naught. So this is outside of the sphere. Okay, and then previously, if we just quickly look on that, this is inside the sphere. So inside, for the result, if it's inside, it's proportional to r. Okay, if it's outside, then it's, oh, actually there's a r square, I forgot. So if it's outside, it's inversely proportional to r to the square. Okay, now we can plug in the number and calculate this again, but E equals 450 times 10 to the minus 9 Newton or coulombs over meters cubed. And in this case, instead of 10, but 6 times 10 to the minus 2 meters. Okay, or actually to the Q. And then divided by 3 times 8.85, 10 to the minus 12 with the SI unit. So we can drop the unit, but you can put that unit in. C square over N times meter square, and then R square in this case will be 10. Okay, so remember, we are using two different R's, but squared. Okay, so at the end, this will be 3.66 times 10 to the second newtons over coulombs. Okay, so this is the second part. Okay, so there's difference when you are inside and when you're outside. This is what you have when you are inside. Okay, and then this is what you have when you're outside of the sphere. All right. Okay, going back to the slide. So if you plot, okay, just the example we had, you'll get that inside is proportional to R, so linear relationship. Outside is inversely proportional, so it goes down. Okay. We'll quickly look at a different example here. In this case, you have a spherical shell. Okay. So for the shell here, thin shell, everything the charges will be on the surface. Okay. So then quickly, we can see that let me just stop this sharing, and then we will see that. So quickly, when you're inside the shell, so R smaller than R, distance from the center of the shell less than R, so your flux is equal to Q enclosed, right? Q enclosed over epsilon naught. And Q enclosed here will be 0 because inside the shell, there will be no charge, okay? So then in this case, E field will be equal to 0. In another case, when R is greater outside the shell, phi is equal to Q enclosed divided by epsilon naught, which is equal to E times A, right? So this will be similar from the previous example. So we'll just quickly go through that. But total Q, that is Q over epsilon naught, then equals to electric field times 4 pi R square, okay? So in this case, then the E field is equal to, so divide both sides by 4 pi R square is equal to 1 over 4 pi. E is equal to 1 over 4 pi epsilon naught times Q over R squared. So this is similar to like a point charge at the center of the sphere, okay? So if you plot it, then this is what you get. Okay, so inside the sphere, E field is equal to 0. Outside the sphere is 1 over 4 pi epsilon naught over the total charge over R squared. So that decreases down, okay? And then on the surface, you can say that's that number. So just replace the small r by capital R. That's what you get, okay? All right, we'll stop here and we'll come back for next time on the Gauss's law. See you guys.